what we're going to do here is to find two examples of the velocity vector, see what they mean and see what way we can interpret them. The first one is the one physics wants us always to do first. So I'm going to say, let's find the derivative, and remember that's the velocity vector, if r of t is cosine of kti plus sine of ktj. If you recognize this is actually just going around a unit circle at some speed. So let's take the derivative first just to see what it looks like. The derivative should be something like minus the sine of kt times ki plus the cosine of kt times k j, like that. Now, two things. Number one, we can do that over here, I guess. All right. We have something that's going around a circle. If k is positive, it's going actually counterclockwise. So the r of t, remember, that points like this. That's r. The velocity vector points like this, which is good. So it's always going to be perpendicular to the radius of the circle, which we always knew. We want to talk about the speed just for a second. The speed here is supposed to be the length of that velocity vector. So this should be the square root of, let's see here, I want sine kt times k quantity squared plus cosine kt times k quantity squared, like that. Boy. You notice we can pull actually a square root of k squared out, so that's just going to be k. What's going to be left is just going to be sine squared kt plus cosine squared kt, and that's just 1. So what that tells us, if we have a formula like r equals cosine kti plus sine ktj, that we get something actually that has uniform speed. It will actually tell us something that's always going around the circle at the same rate. So that's the first example. A second example is the kind of which shows up in a lot of the kinds of calculations we're going to have to do. And that is, if we start out with a function, a plain old ordinary function, say y equals x squared. The first thing I want to do is find parametric equations for it. Remember how we do this usually. We just set x equals t, y equals t squared, like that. And so I'm going to rewrite this as ti plus t squared j. I want to take the derivative. What I'm going to get is 1i plus 4tj, like that. If I'm looking at the graph, y equals x squared just looks like this. Let's pick a point to plug in. How about 2? So what I'm going to get is 1i plus, looks like I want 2tj here, not 4. Yay, better. Here's where I get the 4. So I get 4j like this. So if I'm at 2, and I look at the velocity vector, it goes over 1 and up 4. Remember, it goes over 1 and up 4. For this, that means the slope of the tangent line is 4 there. And the speed is going to be something like the square root of 17. Now remember, the speed depends not just on the graph, but how fast we're actually moving along the graph. So that depends on how we decided to parameterize that function. But those are two nice examples, moving at constant speed around the circle, and what happens when you try to look at the velocity vector of a parameterized function.